Hi everyone, my name is Arshita Gupta. I'm a senior research engineer at Samsung Research America. Today I will be talking about our work, torque-based structured pruning for deep neural network. In order to accelerate CNNs, structured pruning is a popular way to reduce the parameters and flops in them. Current structured pruning techniques often need one or more of the following requirements. With these requirements comes their unique challenges. Some of them require modifications to the original architecture, such as addition of batch normalization layers. Often, the addition of such layers can be detrimental to downstream tasks such as super resolution. Sometimes they require a pre-trained model as a starting point, which is not always available. Some of them require integrations of paradigms such as reinforcement learning or implementation of intricate gradient update rules, which can be too complex to implement. A lot of times they require repetitive training, pruning, and fine-tuning stages. They require step-by-step pruning of each layer instead of a global pruning technique, or require training of distinct models for specific pruning ratios. All of this can be really time-consuming. Our goal here is to get rid of the requirements mentioned in the previous slides. Mainly, we want to prepare a CNN model for pruning by creating an ideal pruning setting. What I mean by this is, let's look at the plot on the right. Here, we have the distribution of weights in a given layer L. On the x-axis, we have channel number, and on the y-axis, we have sum of the absolute weights. As you can see in the top plot, the distribution of the weights is even throughout the channel number. However, we want to create an ideal pruning setting where we concentrate all the weights around a given point. And as we walk away from this point, we increase the sparsity in these channels. This will allow us to prune at different pruning ratios without loss of much information. And very less repetitive fine-tuning steps will be required. All of this we want to achieve without any modifications to the original architecture. So how do we redistribute the weights that changes with distance? To achieve such a distance-varying force, we exploit the concept of torque from physics, whose strength is dependent on the distance from a fixed hinge or a pivot. As you can see from the diagram below, we have the hinge and we have the door attached to the hinge. When we apply force directly on the hinge, there is no torque. However, as the distance of a force increases from the hinge, we see the amount of torque also increases. We now use this method in our pruning technique. We fix a hinge or a pivot channel P in our CNN layer. During training, we apply a force such that its effect is strongest when farthest from the pivot channel. The effect here is observed in the form of sparsity. Higher the torque, more sparsity will be induced in those areas during training. In short, we are compressing all the information around a pivot P. During training, we can either start from random initialization or a pre-trained network. Let's look at the implementation. Here we have a CNN layer L containing n channels. We fix a pivot channel P. In our case, we fix the 0th channel. However, any channel can be used. We define Wn as the nth channel weight, and we define Dn, which is the relative distance between the nth channel and the P channel. Mathematically, we look at the gradient update rule for channel n, which is described by equation 1. We introduce torque by adding an extra penalty term on the gradient update rule. As you can see, it is highlighted in the red box in this equation number 2. Lambda t is the torque rate controlling the degree of compression, and we will discuss about the effect of lambda t in the next few slides. Next, we derive the torque T given by the product of W and D. This D can be any monotonically increasing function. Inserting 3 into, what we finally get is this updated rule, which is a product of lambda T, the Dn, and the sign of the weight matrix. Effect of torque training. So if we start with a randomly initialized model or a pre-trained model, we train it with this updated rule, gradient update rule, and what we see is that after training we have compressed all the weights to just a few channels near the pivot point, and then it is easier for us to prune it. Now let's look at the effects of lambda t. So as you can see here, as we decrease the amount of lambda t, the compression also reduces. This is actually an experiment with layer 14 of VGG19 trained with torque. At lambda t equal to 10 to the power minus 6, we see a very high compression, and you see very less channels are activated. However, as we reduce lambda t, we see that more channels are now activated. Like we talked before, fine-tuning can actually take up a lot of time. In our torque-based training, we show that for a lot of for a high amount of parameters pruned, we actually don't require any fine-tuning. So as you can see here in this plot, we have trained a ResNet 164 on CFAR 100. On the x-axis, we show the parameters pruned, and on the y-axis, we show accuracy without any fine-tuning. In this plot, the purple X, the red square, and the green inverted arrow is our torque trained models with different lambda t values. And as you can see, even at a very high percentage pruned of more than 70%, we see hardly any loss in accuracy. These are our results for ResNet 56 on CFAR 10. We have this time compared accuracy drop with the speed up as well as the percentage parameters pruned. Here we have two values, R and P, which correspond to training a model with torque when starting from random initialization or from a pre-trained model respectively. As you can see from the table, our torque trained models actually outperform many of the state-of-the-art structured pruning techniques. Only in one particular point at 2.3x speed up, we see that RLMCTS actually does a little better than our torque training. However, we would like to remind here that RLMCTS uses reinforcement learning and has to train this model with their original model, and which is a very tricky technique, while our torque technique is very easy to implement. In summary, we propose torque-based structured pruning, which can effectively reduce flops and parameters while maintaining high performance of the model. We compare our method with current state-of-the-art techniques on multiple datasets and show superior performance. Our method is easier to implement and requires no alteration to original model architecture. Furthermore, it can be applied to either a randomly initialized model or a pre-trained model. Our torque-trained model can be pruned at different levels of sparsity without the need to retrain. Until a certain sparsity level, the compact model created by our method after training shows good accuracy without any additional fine-tuning steps. Thank you.